This one here? Come on. Thank you very much, Fabio. So Fabio has given you the details of his extraordinary machine, which is a beautiful piece of engineering, which you can see over there. And as I keep telling people, it should really be in the Museum of Modern Art. It's such an exquisite piece of design. So we decided to plant it here in this off-the-grid, rundown chalet, farm actually, at 1,000 meters elevation in the French Alps. So there's no electricity. The sanitation is natural sanitation, and as you can see, this house is going through a deal of renovation, and it's now a center of demonstration of different technologies that are applicable to regular people. Nice place for a workshop, nice place for an away day, and then to, you know, focus on the matter in hand and then see how it's applied in nature. One thing that's intrigued me from the beginning is that as a journalist by background, we recognize that in the political landscape of Europe, not to mention the rest of the world, there's an enormous problem of housing. There's an enormous problem of impossibility of young people buying houses of any sort, whether in a city or in the countryside. This is actually taken from a recent Le Monde article about how there is political unrest, there's political tension in France, Sweden, Spain, UK, Poland, Ireland, Netherlands, Greece, Portugal. You could probably name every single European Union country, not to mention others, where the children of the people sitting in this room will not be able to afford to buy, not to mention rent accommodation, because of what's happening, because of the inflation in prices, because the tourists who are coming in through Airbnb. It's a crisis which is affecting the body politic of Europe. And if you think that's not important, just take a look over the pond to America and see what's happened to a society where the body politic has turned toxic because of perceptions of what they can afford to do or what they can't afford to do. So as we know, young families are locked out of housing, there's sky-high prices, there's excess tourism. Above all, there's really crappy housing stock. You know, 50-year-old houses that weren't properly built in the first place have to be retrofitted at an enormous cost to people who just can't afford it. And you have the rise of the eco-anxious, whatever they may be, the people who are turning toxic in their politics or just turning to despair. So in that landscape, we bought this little house in the middle of this beautiful space in Haute-Savoie, halfway between Chamonix and Geneva. Extremely affordable because it's in a natural off-grid location where there's no other building allowed. This is the town, Samois, in France, where down at the bottom, where the village is, where the town is, it's kind of mega crazy prices, 1 to 5 million euro for a house. So none of the local people can stay there. Their children can't remain there. They have to commute 30 kilometers in to the village where they were born because expatriates are buying ski chalets. They're sticking in big-ass oil tanks. They're consuming 3, 4, 5, 6 tons of fuel a year, and there's zero appreciation of the damage they're doing, not only to the local environment, but to the planet. Up here where the blue dot is where my little place is. So it's in the watershed of the town, so the builders can't get their hands on it. They can't develop it. And as a result, you know, we bought it for a small amount of money. And it has challenges. There's one of them. This is December of this year. Try solar when you've got 10 inches of snow on your panels and the panels are on the roof. How are you going to do that? Solar panels are extraordinary. They're fantastic. We love them when they work. When they don't work, what are you going to do? But with this machine from Fabio, which won an award last night, so we had to rapidly update this presentation to reflect that, we have ample heat, surplus electricity, and biochar, which means that you can have a city-style apartment level of comfort in an area like this. So this, I'm just here to really tell you that the end user is the important person. You know, we can pump out biochar day and night, but if it's not helping the little guy, if it's not helping the society to kind of advance, if there's not ways into doing that, you're sort of not wasting your time, but you're maybe missing the target. In this area, we have 100% autonomous energy. We have zero pollution emitted thanks to this machine. We have backups, so we have fireplaces, we have wood stoves, we have the whole 9 yards, but we don't use them. So our emissions are not only carbon neutral, but we're not breathing in toxic fumes from beautiful wood stoves. We might do it for Christmas Day, and that's kind of it. And we produce approximately a ton of biochar per annum. Now that's the kind of, turns out to be the interesting bit. It isn't what we didn't start out trying to make biochar, far from it. We started out just trying to find a solution to a problem. The problem was, how do you live comfortably off-grid without having to prepare the wood to put in the fire 2 years before you lit the fire? Well, who does that? You know, it's kind of from another century. So I'll get to the point in a second. This is it. This is a little machine that belongs in the Museum of Modern Art. It's clean, it's quiet, it's inside the house. The exhaust is a plastic pipe. It's quiet as a dishwasher, a noisy dishwasher, but it's still quiet. And it produces 1 kilowatt of electricity per hour, 6 kilowatts of heat, and about 1 kilowatt of biochar per hour. Now, this is the bit I would like you to think about. I'm sure wherever you are from, especially if you're from Europe, there are brownfield sites all over the place. Read any newspaper, the factory's closing down, it's moving to Asia, they're not making this anymore, there's 1,500 jobs just been let go. There are brownfield sites everywhere. They might be toxic, they might not be toxic, but the real estate value is infinitesimal. It's a little bit like my field in someone's. It's available. The regulations are changing regarding tiny houses. The knowledge is there with passive houses. It's going to take some thinking out of the box to think about how can we change the equation for these eco-anxious, frustrated people who are going to tear down the house if we don't find a solution for them. Think about solutions like this. Collaborate with municipalities, find the kind of industrial site within range of a city, a town, or a municipality, and get the architects and the builders to get busy and think about on or off-grid generation of power, or a combination. His system combined with the grid resolves all your peak power problems. So you're actually paying very little for your electricity because you're producing the peak power when you need the peak power, and you're getting the heat all day long, or the cool, as it may happen. Here's a little example of what could happen. So this is the Biochar eco-village in the Netherlands. They've built, it's mostly built out. They've just won the SDG awards for sustainable architecture, I think. Sustainable Cities and Communities Award, which is a tough one to get. They won the most sustainable business in the Netherlands award from the Dutch construction industry. Not exactly the friends of the greenies, right? But they voted these guys the most. So why were they doing it? Because they're talking about affordable social housing with a good biodiversity impact. Now, they don't have the machine we're talking about, but you could imagine with the machine how much more powerful this could be. So it's kind of, it's the dream of municipalities to find homes for the local people which don't turn into ghettos and nasty places and places of crime. And that's what they're finding when you create an environment where people can do some gardening, use the biochar, learn about nature, learn about biodiversity. It suddenly turns a corner. So the municipalities are super interested in it. They've changed Dutch legislation to enable these guys to use innovative things that are not quite ready for the market. So there's something here. There's something, I think, for people to think about how can you move this into the general population and away from the experts who've been sitting on these panels, and they've been fascinating panels, but they are for the experts, really. We need to get it into the general population. This is our attempt to do so. So here's the benefits of biochar. You can see some outstanding growth in the right-hand corner. So every year we have a festival called the Fête des Possibles. It's in Belgium and France for the moment. It takes the entire month of September, and communities showcase different ways of living. So here we get about 40, 50 guests a year, and we're demonstrating to people the potential of investigating different techniques of being more autonomous. And indeed we are. And just to conclude, I can tell you as an end user, not a technician, somebody who's had to learn the hard way how to do it properly, that it turns out actually that biochar is the key that we didn't know we needed and that we didn't know we had. And so it's opened the door to affordability. It's opened the door to maintaining and improving biodiversity. And as we're learning year by year, it's creating extraordinary benefits in soil fertility and growth and potential. And we can see it by the numbers of ordinary people who are coming to our events every year. So this is it. Just want to sort of open that new window to you, if it is a new window. Thank you.
If there are any questions or any points you want to clarify, we are here.
Thank you very much. My name is John McGarrity. I'm a reporter with Quantity Intelligence. Excellent presentation from the both of you, really interesting. The question would be, to what extent can local authorities in various European countries partner on incentivizing a plan to use biochar in home heating? I mean, is this possible, and have you had any engagement with local governments or urban planners on this? Thanks.
It's a difficult point because actually the biochar, for example, in Italy, is difficult to be identified by an exact politic. And our customer use it on the garden, mostly. The amount is very small, and so in this moment, a small amount of biochar production doesn't make sense to make carbon credit certification, for example. It's a huge work and doesn't make sense for each small producer. Or you have a very big amount of biochar, or it's better to use it on the garden and forget for carbon credits. There are many quantities of possible use. If you go to the HR pavilion, you will find many different applications and soil improving. But in this moment depends on local politics, and I can see a very slow increasing of interesting. Maybe we'll start from people, and so maybe some central government will decide something on it, but it's another point, yes.
Just on the same point, there's a lot of resistance. A lot of resistance due to ignorance, I would say, and also just due to the pure inertia of the market. So a product like Fabio's, for example, a cogeneration product, is not really interesting maybe to a boiler maker because they're making too much money selling obsolete boilers into the market. A municipality, they don't have the expertise, so they'll talk to a consultant, and the consultant will tell them what the boiler maker says to say. So I think there's really kind of difficulties in the market, the stickiness in the market. And on top of that, there's a lot of, how will I put this politely, the bureaucracy of any country, but particularly in European countries, is quite centralized. And there's quite a lag between the kind of edgy, innovative things that are happening and what somebody who's making decisions but has no real life experience in this is going to say. So we've had pushback from the environment industry saying, Why would you do this? Electricity is already inexpensive and decarbonized in France. Why would you do this? You're just going to cause stress in the market because you're going to be competing with the pellet stoves. So people not looking at the benefits, looking at the negatives, and the result of that is a kind of stasis in the market. And so what you would think would be creating a lot of fizz of excitement and activity and interest actually is flatlined. But I think over time, and thanks to conferences like this and to the awareness of smart journalists like yourself and the word getting out, people will open to it.
A question and a comment. The comment is, I don't think it makes sense to sell 1 ton carbon, or 2 tons of carbon credit. I mean, this is the way for that person to actually achieve carbon neutrality for all the other parts of their lifestyle that they can't decarbonize. So I don't think you should even pursue that. But I have a question on one of your slides, Fabio, that was talking about something puffer, and I don't know what that meant.
He was told, he already told me that English people use
He paid me to say this.
use a different term. Is the hot water tank buffer, but technically it use puffer, but is the way to store energy with a hot water tank. Yeah. Okay. Hot water tank.
We might have to ask you questions and make this interactive. So does anybody have any direct experience in the room in making biochar in the garden, or any experience in trying to co-generate or figuring out insulation or trying to work through a more autonomous lifestyle?
So, yes, we're from Karelian Bio, from Finland, a biochar producer, and we started our experiments with a cone-shaped flame-coated kiln. So, yeah, we have in a 200-liter kiln scale experiences where we started and where we started to. Kind of a experiment with this biochar production.
So where did you say this is?
Excuse me?
Where did you say?
We're located in Finland. Yes, in eastern corner of Finland.
The picture you saw in his presentation about the installation of the unit in the green room came from a customer in Finland,
Okay.
Martiniaru, if I'm not wrong.
Okay.
Martiniaru.
Yeah.
It's there is a nice guy like Leonard who buy a unit and is making energy and biochar also in Finland.
Okay. Yeah.
Maybe you can visit him.
Yeah. Probably. Yeah.
Thank you very much. If there's no other questions, I mean, we'd be delighted to talk to you bilaterally if you're too shy to speak in the format of the meeting. But thank you so much for your attention, and all the best.
Hello, good afternoon. So I was awaiting a moderator for this session, but I got aware that there is none, so I start right away. Sven Jensen is my name. Here I'm the other co-speakers afterwards. Very good. So Sven Jensen is my name. I'm representing the company Dürr. We heard a lot about producing biochar these days, yesterday, today, and also using biochar. I want to add another aspect to that, and that is improving biochar production by using the waste heat. What is this? Yep, right. So here, a short overview. I will say a few words about the company, then specifically about the technology. It will be that part will be a little bit technical, and then I will specifically share with you how we can apply the technology to the pyrolysis installations, to the pyrolysis industry. And then in the later part, maybe I have to hurry up anyways to keep the time. We have a couple of references, but if I go over that one quickly, you can, I guess, receive the presentation later on and then just look it up. And at the end, the summary. So the company Dürr, we are a German-based company in the southern western corner of Germany in the area of Stuttgart. We are a medium-sized or bigger company, 18,000 employees worldwide, because we do a lot of things. We are a specialized company on machine building and also plant engineering. What is here in the middle, framed with a green bar, that is the Clean Technology Systems division, and we, with our product ORC, Cyplan ORC product, are part of that CTS division. Dürr has a big interest also in becoming more sustainable. It itself has a certain policy, and we are also, with our Cyplan ORC product, we are basically enabler for the customers also to join this journey of more sustainability. So what is ORC? ORC stands for Organic Rankine Cycle, and in a nutshell it can be considered similar to a water steam cycle. So technical people among you may know this. So this is the cycle what happens in big power plants as well. Thermal energy is heating up a media. In big power plants it's just water transforming to steam, and this is sent to a turbine. Well, then in the end the electricity is generated. And basically we are doing just the same, with the small difference that we are not using water because it has a relatively high boiling point and needs high temperatures, but we use organic working media which have a lower boiling point, so we can tap on lower temperatures. But again, relatively the same. We evaporate, we send it to a turbine. This is the place where we generate electricity. And thereafter, we are at low pressure and lower temperature in the ORC media. We need to take out some thermal energy in order to bring it back into liquid stage, the ORC media, and then close the cycle with a pump. So this is very quickly speaking and explained what it is about. The installations, the smaller sizes look as here in the pictures on the right-hand side. So modular units, we try to squeeze everything on basically the footprint of a 20 or 40 foot container. So they are completely assembled in the factory and then sent to the customer and installed there. Because of that, obviously at site there is little cost for installation, and also the commissioning is then quickly done. We distinguish between high temperature ORC and low temperature ORC. On the left-hand side, from bottom to top, this represents a little bit how we receive the energy. So when we receive the energy just with hot water, what about 90 degrees or up to 120 degrees, this is the area of low temperature ORC. The cycle is basically the same as explained before. At the condenser, definitely you have to cool at a maximum low temperature what is possible, and that means most of the times you just have something like a cooling tower or a dry cooler where you push this condensing heat into ambient air at low temperatures, 15 degrees in wintertime, whatever, 30 degrees in summer, just what you can technically establish. When we go to other media, when we receive the heat by means of thermal oil or even hot gas, then we talk about high temperature ORC. And here we have two differences. So clearly one is the temperature is higher, as it is easy to follow. And due to that, we have higher efficiencies in the system itself. So roughly double the efficiency compared to low temperature ORC. And additionally, we can run the condenser at different conditions. So we can perform the cooling of our ORC device with hot water. So that means, for example, we can be integrated in a hot water loop where we receive hot water at 50 degrees or 60, so the return from any heating network. We push it up, the temperature to 80 degrees or even 90 degrees, and then send it again to the consumers. And in these cases, we talk about the high temperature ORC being a combined heat and power unit. At the heart of our technology, there's a turbo generator. Here, I don't want to spend too much words and explanations, only to take with you, this is a hermetically sealed turbo generator, and that means the organic working fluid, what we use, cannot escape. Not at this place and not at any other place of the ORC system. Here is a small picture on the left-hand side. These are the typical sizes what we have as modules. So the number stands for the electrical production. 50 kilowatt is the smallest unit, and the 500 kilowatt is the largest transportable unit. So in one piece, that has really the size of a 40-foot container. When we then talk about the application of the ORC for industry, and clearly not only pyrolysis systems, but it can also be for big industry, steel or any other glass factories. They have a lot of waste heat. Then we are in the on the right-hand side, and there we rather tailor the ORC solution to the customer needs. So by to whatever media the heat is available, we can try to, or we deliver the equipment to catch the heat and then send it to the ORC unit. So now, what does it mean for the pyrolysis industry or for creating biomass? Here in this flow sheet, very simple with few boxes, as material is received and then sent to the carbonization plant, and then more in dotted boxes on the right-hand side is whether there is a filter and a gas cleaning equipment or not. That depends on the mode of the pyrolysis. And in the end, the exhaust gases go to a stack. I've developed this example on the basis that we receive biomass, so wood chips in this case, with a water content of roughly 35%. However, most or many, all of the pyrolysis plants, they work better if there is a lower moisture content in the biomass received or introduced into the reactor. So then, if wanted, then or desired, then there must be a kind of drying system in between. The ORC typically is then at the tail end. So after the pyrolysis and the combustion of the syngases, we have a hot flue gas. And this is exactly where we want to place the ORC unit. So we take the hot gases directly into the primary heat exchanger and run the cycle as explained before. I skip a little bit or speed up. So what we do is we produce the electricity, again, as explained, and by here this rough example that with this input or a typical plant, the plant itself from beginning to the end consumes roughly 30% of the electricity what we generate. So the remainder, 70%, is basically free for use or for any neighbor who is there or for sell to the grid. And similarly, I explained before that we can run the ORC as a combined heat and power unit. So we have this secondary heat, and part of that we funnel back to the drying unit. And in that sense, we really close the cycle and make it a very integrated system that we use the temperature up to 90-95 degrees for drying the feedstock in the front. And again, clearly depending on the water content of the feedstock, there is still temperature or energy, thermal energy in surplus, roundabout in the range of 50 to 70%, which again can be used externally or sold to any district heating network. So we are lucky that we could convince already some of the pyrolysis producers. So we have a project together with the company Pyrex. Has been installed in Germany, in north of Germany, and is running since roughly 1.5 years. So 2 lines where we have added a ORC 120 to a Pyrex 1500. Then another German manufacturer, CTS Schuster, so they are building a plant in Switzerland, and there it's a bigger unit. They have a different technology, and here we also have a bigger unit, which then rather looks like in this illustrated picture on the right-hand lower side. This is then the ORC being composed of a standing evaporator, and then the ORC base module, but still the concept is the same. So we take the hot flue gases. Then we are working also on a project in the USA. Due to certain circumstances, it's becoming more and more interesting also for US producers to take care about their waste heat. So we are very lucky and proud. This will be, it's in the final stage of being manufactured here in Germany and then shipped over basically in the month of May. And then one another, again with a partner, I forgot, so previously in the project in the US we have with the German company Carboforce. And finally here the 4th project which we also have, or which is very close, with the company NGE, which is also present here, again in Switzerland. Different technology on their side, adaptation on our side, but the concept is basically always the same or similar. So I don't know. Thank you. So here are then some more references. Overall, clearly we are a German company. Most of our installations are in Germany. But we also have a couple of installations outside of Germany and also worldwide, where we, due to certain reasons, could convince the customer to pick us. Then here there are more pictures I flip through very quickly. We have a lot of installations in the biogas sector, which might also be interesting for other people here in the back of the hall, but which are probably not sitting here. Also larger units where we have this, what I explained, the transfer with thermal oil. When there is a boiler, just a biomass boiler, heating up the thermal oil, and we receive it at temperature of 300 degrees, for example. and also a classical industry. Here's a picture of a then larger plant in the steel industry. Here we capture the exhaust gas from a reheat oven. Yeah, here I just assembled a little bit pictures from a screenshot from the screen. You see, and it's not really falsified. So it's 500 kilowatt zero, but it's the reason for that is that we limited. So we are basically reducing the heat intake when we reach the 500. This is why it's written here on this display. On the right-hand upper corner, you see very different points of operation. So each dot, blue dot, is 1 point operational point. And the red line is what we promised contractually to the customer. So what you can see is that we here achieved what we have promised. And in the lower corner is also just an image that how ORC performs. So it's not only functioning at steady state, but also when the heat source is fluctuating, so going up and down, and then basically the ORC system is following it. If it falls below certain values, clearly then we have to switch off, or well, the ORC switches off itself, not enough energy to produce electricity, but then it's coming online all automatic, so without manual interaction or so. Right, then I'm at the end. Just a short summary. So what are the big benefits of the ORC? So you can produce the electricity on site, CO2-free electricity, because the CO burden is not connected to the waste heat and therefore not to the electricity. I didn't talk about that point a lot, but we are using natural hydrocarbons as ORC working media, so no refrigerants. That means we have a low GDP and global warming potential, and also we think we are safe for whatever development might come in relation to regulation of refrigerants. Yeah, clearly with the electricity generated, you don't need to buy it from the grid, so this is the main point of saving. In case of the pyrolysis plants, of course, as well, the electricity is CO2 free. If you buy the electricity from the grid, there's a certain CO2 package coming with it, and normally with the certification process you need to deduct. So whatever you have spent in CO2 for your production or for carrying the biomass to your plant, and with producing your own CO2-free electricity, you basically can increase or improve your case here. So we can use the condensing heat on a high level, so provide secondary heat, for example, for drying purposes. And eventually also the ORC technology as such, as it is quite innovative, is in many cases, in many nations, a trigger for subsidies or feed-in tariff or similar. So, thank you very much. That's the end of my presentation. And please, if you have any further questions at the end of the round or then later, I'm also at the booth G44. Thank you.
Okay, yeah, now we will switch the topic a lot, so I'm not a technician. So yeah, I'm a scientist. Today I will present you my first peer-reviewed paper It will be about the global potential of biochar as a soil amendment. So with my first peer-reviewed paper, we analyzed the impact of biochar as it could have on as a soil amendment. Yeah, first I will introduce you to the topic, why we start focusing on that, our methodology, and yeah, I will, in the end, I will also present you our results. So first of all, so here you can see yeah, global maps on regions that are already facing aridity today. So aridity means that means a region where we have less rain than we have evaporation. So more than 50% of the global land, especially of the agriculture land, is already facing this issue of aridity, and it's growing due to the climate crisis very quickly. And as an effect, so there is a link between the climate conditions and the soil conditions. So the more aridity we get, so the more regions, the more agricultural regions that are facing the issue of aridity also degrade. So the degradation of soil means that it reduces the agricultural productivity. So it loses the soil structure, it's getting more dense, and it's getting much harder to grow crops there. But fortunately, biochar is recognized as an option to overcome those challenges, because it has an impact on different or several physical, chemical and biological soil properties. For example, it has a very high pH value, so it increases the pH value, and it also has a very high specific surface area, and therefore it works like a sponge, and it holds water and nutrients much better and much longer, especially for very bad soils. So especially in regions where we have very poor soil structure, biochar can really enhance the soil structure a lot, and therefore improves the yield. But in the current literature, so there are many research done about this, but what we see in the literature is a very wide range of the impact that biochar can really have on the crop yield. So we have many researchers that even show a decrease in crop yield where we added biochar to the soil. So a meta-analysis shows that sometimes the yield was less than half compared to the field without the biochar, because the carbon content was already very high in this region. And on the other hand, we have researchers that showed an increase in crop yield of more than 300%. So here I just took 5 little examples where we can see the yield, the impact on the yield. So for some researchers it was -18%, -24%, and sometimes the yield was more than doubled. The reason for this is that those researchers were done in different regions in the world. They took different biomasses for the biochar production. They implemented a different amount of biochar. We've been in different climate classes, and we planted different crops. Therefore, it's very difficult or almost impossible really to compare from the current literature what the biochar really influences the crop yield. Therefore, our aim was to somehow get a strict value chain, so to have a global comparison. Okay, we have this biochar. What does this biochar impact which crop? Therefore, the research gap we faced in our research was where in the world we have the high potential for biochar as a soil amendment. For that, to start with, now it's getting a bit theoretical, but just to explain the methodology we used. So there are satellite data, and with those satellite data we know the soil and the climate characteristics everywhere in the world. So we know, for example, with satellite data, the pH value here in Nantes, in Paris, in Berlin, in China, everywhere, and as well as the carbon content, the sand content, the silt content. So we can analyze all that with satellite data. And we took those data, so we took the mice yield, so we don't know this only about soil characteristics, but also, for example, for the mice yield for climate data, and we used those data with a raster of 0.1.0.1 degrees. So in total, we had 6.4 million data points, and for each data point, we knew several climate and several soil data, and we also knew the mice yield, and therefore we used a supervised machine learning algorithm in order to better understand the correlations between those input data of the climate, the soil and the fertilizer data, and the mice yield as the output. So in our first run, we tried to find the correlation between those input data from the soil and the climate data and the mice yield. And then in a second step, we asked the model, okay, now let's assume we would implement biochar everywhere. How would the soil properties change after the addition of biochar, and what impact, or then in the second run, what do you think with those new soil data, how would the mice yield increase or decrease, and how much does it increase or decrease, in order to get a global map which can show us really the impact of biochar on the mice yield. I will get now a bit more, because it's you can see it very properly, I think, but I just want to explain you quickly, because there's no really sophisticated model that shows the correlations between biochar and the soil characteristics. So we work very closely together with our department from the soil science. So we linearized the model of 14 studies in order to find the linear correlation between the pH value, for example, the cation exchange capacity, the bulk density, and the soil organic carbon content of the biochar and the soil. So we found these 14 researchers that measured the impact of those soil properties on the impact of the biochar on those soil properties, and then in the end, how we used it in our model. We said, okay, the pH value that we have now afterwards, after the biochar implementation, was the one before, plus this factor multiplied with the pH value of the biochar minus the pH value before. So this is just the linearization that we took for our model. The biochar we assumed was from our other department, where we used our laboratory data from Miscanthus biochar that was pyrolyzed at 400 degrees for 3 hours with those input data. The results can be seen here now. So what we see is first of all that we have a very wide range of yield increases or yield decreases. In general, in Europe, we see a very low impact of biochar on the mice yield. So the average impact was even -2%. So adding biochar to soils here in Europe would, assuming to the data that we took from 2010, would even decrease the mice yield. Therefore, it would not have a positive impact, and this is also what we hear from agriculture experts, is that for example in Europe or in Germany or in France, that we don't see a very huge potential for the agriculture market, because we already have a very huge mice yield, and biochar does not really enhance the agriculture here. But this is very different, especially in arid regions in sub-Saharan Africa or in Southeast Asia. There we see a very high potential. We can predict a yield increase by 50 to 100%, which is already validated. So we can really see that that in those arid regions, biochar can really enhance the crop yield much more than it does here in Europe or in Germany. Yeah, okay. This is just a short validation we did with partners from Turkey. So they did a GIS MCDA model for the suitability of biochar as a soil amendment. We can see some similarities in their results and our results. So we see a very low potential in central Anatolia, so in central Turkey and the southeast region of Turkey, and we just see very low potential in some areas near the coastline in the north or in the east or in the south of Turkey. So this was just to in order to compare our results with the results from this study. We also validated our results with field studies from China, Zambia, Germany, Australia, and Burkina Faso. What we can see here, so what we compared for each study, how much biochar was applied here, and what was their result, what the biochar really has for impact on the maize yield. We see for 6 out of 8 studies that our results were of the prediction of the forecast were quite close to what the field study has shown. So this was the case in China for the first study in Zambia. The second study we could only show the trend, but so we cannot take each referent field one by one, because those fields are usually very small, and so we would need more validation fields in order to be really sure. Or to really validate our model, but this table should just show, so these were all the studies that we found, that the forecast that we took with our model were at least very close to too many of those studies. Yeah, maybe just to sum up or to conclude our results. So we developed a model with a random forest machine learning algorithm to find the correlations between climate, soil, and fertilizer data and the maize yield. The potential for biochar in agriculture in Germany and Europe is very limited, but it maybe somehow might develop in southern Europe because of soil degradation that is already going on there, and desertification. But what we have is a very high potential in the global south, so we should investigate and invest more in the biochar production for agriculture in the global south rather than Europe. And that for Europe we would need to investigate more different value chains. So for example, biochar in the metallurgy, what we saw this morning, in the concrete production, or as a concrete additive for horticulture or whatever, but that the agriculture potential in Europe is quite small compared to other regions. But what we would need in order to be really to use this model more is we need more validations. We would need bigger fields and more validation points to compare the results better. We need more explainability for the machine learning algorithm. We need a sensitivity analysis for some parameters, and the model that we have developed for the correlations between biochar and the soil properties is also still under development. There's a lot going on there in the research field, and we need also to integrate the production cost rather than just the potential of biochar as a soil amendment. Yeah, so those are the references. And afterwards, I'm still open for questions if you have any. And thank you very much for your that you are here.
Bonjour à tous. Donc, je m'appelle Yann Le-Brech, je suis chercheur à l'Université de Lorraine et j'ai eu l'occasion de travailler pour un projet ADEME donc, qui s'appelait Qualités, physico-chimiques et potentiel valorisation des biochars, qui a été un projet qui a été financé par l'ADEME entre 2020 et 2024, dont l'objectif était l'évaluation du potentiel agro-environnemental des biochars et la caractérisation des biohuiles de pyrolyse. Donc, il y avait deux partenaires dans ce projet. Le premier, c'était Ritmo, qui a effectué des tests agronomiques, et le LRGP, où on a effectué la production et la caractérisation des biochars en collaboration avec l'IS2M, l'Institut des sciences et matériaux de Mulhouse. Donc, ce projet, il abordait 4 points. Le premier, c'était le bilan des technologies et capacités de production de biochars en France. Le deuxième point, c'était la production et la caractérisation physico-chimique des biochars. Le troisième point, c'était donc l'évaluation agronomique des biochars, notamment un focus sur la dynamique de l'azote et du phosphore. Et le quatrième, c'était la production et étude des biohuiles de pyrolyse rapide. Donc moi, je vais vous présenter les 2 premiers points sur lesquels j'ai personnellement travaillé, à savoir la production de biochars et caractérisation et la production de biohuiles de pyrolyse rapide. Donc la méthodologie était la suivante. On a commencé par une sélection de biomasses qui nous ont semblé représentatives. On a divisé en 2 groupes, donc les biomasses qu'on a appelées les biomasses lignocellulosiques, donc du hêtre, du chêne, du douglas et rafle de maïs, et des biomasses non lignocellulosiques, donc fientes de volaille, fumier bovin et digesta. Ces biomasses ont été pyrolysées donc, dans un réacteur tubulaire à l'échelle de dizaines de grammes à 500-800 degrés à 2 régimes pyrolytiques, un lent donc à 10 degrés minute et un autre rapide à environ 60 degrés par minute. Ces biochars ont été caractérisés donc, au LRGP et à l'IS2M, puis étudiés en test agro chez Ritmo. Donc, les propriétés physico-chimiques qui ont été étudiées, donc d'abord les compositions chimiques absolues en analyse élémentaire et proximètre, des analyses de fonctions chimiques, des analyses morphologiques et des propriétés mécaniques. Et les propriétés agro-environnementales, c'était plutôt donc, la cinétique, libération de biodisponibilité, azote et phosphore, et la biodégradation du biochar dans les sols. Donc tout d'abord, quand on s'intéresse à la structure et composition des biochars, on peut facilement donc, avoir une information avec le rapport H sur C et O sur C, qui sont des valeurs assez faciles à obtenir par analyse élémentaire. Ce qu'on observe, c'est que en fonction de la température, donc là vous avez les résultats pour la pyrolyse rapide, en fonction de la température, on vient concentrer le biochar en carbone, et en fait on a différents seuils qui sont en fonction de la température. Vous avez à droite par exemple le rapport H sur C en fonction de la température, et on suit finalement une corrélation. Donc en bleu vous avez une corrélation qui est issue de métadonnées sur des centaines de biochars. En bleu vous avez nos différents points, donc on voit qu'on suit bien cette corrélation. En rouge et en vert vous avez 2 points, ce sont des points sortis donc de corrélation de littérature. L'intérêt de ce rapport H sur C, c'est qu'il permet d'avoir une estimation de la taille des clusters, donc de la stabilité du biochar dans le sol. Et on peut voir que du coup à 800 degrés, on obtient des biochars qui auraient théoriquement des tailles de 12 par 12. Ceci dit, cette technique ne permet pas d'avoir une idée réelle de la structure du biochar. Donc un autre test qui permet aussi d'avoir une idée de la stabilité du char, c'est la mesure donc, du carbone fixe. Donc ici vous avez les différentes mesures pour les biochars obtenus en pyrolyse rapide en DAF, donc en dry ash free. Ce qu'on observe, c'est que lorsqu'on augmente la température de production, on augmente la quantité de fixe carbone relatif dans le biochar. Ceci dit, si on compare par rapport au rendement en carbone fixe, donc c'est par rapport au carbone fixe de départ, on se rend compte qu'en fait c'est assez stable, c'est-à-dire que la quantité de carbone fixe produit par rapport à celui qui était au départ reste relativement stable. Et une observation, si on compare les différentes biomasses, c'est qu'on voit que les biochars issus de biomasse non lignocellulosique présentent un taux de fixe carbone plus faible comparé aux biochars de biomasse lignocellulosique. Donc après, on s'est intéressé surtout à quelle était la structure de ces biochars. Donc on a fait des tests en résonance magnétique nucléaire. La résonance magnétique nucléaire permet, donc du carbone 13, permet d'avoir une idée des fonctions chimiques, donc de la structure du carbone à l'intérieur du biochar. Et on a vu par exemple pour 500 degrés, vous avez donc des teneurs environ de 90% en carbone aromatique, et à 800 degrés on a des teneurs de quasiment 100% de carbone aromatique. Donc ces observations sont cohérentes avec la littérature, puisque 500 degrés c'est la température à peu près à laquelle vous commencez à avoir une teneur proche de quasiment 100% de carbone aromatique dans votre biochar. Ceci dit, ça ne permet pas d'avoir une idée très précise de quelle est de la structure réelle de ce biochar. Donc on est parti sur une autre technique, qui est la technique de mesure par spectrométrie Raman, qu'on a effectué donc du coup à l'IS2M. Donc la spectrométrie Raman, elle a été très utilisée sur les structures carbonées et elle a été appliquée récemment sur les biochars. Quand vous faites une analyse en spectrométrie Raman, vous avez deux pics d'émission, un pic D et un pic G, et le ratio, l'intensité de ces deux pics vous permet d'avoir une idée de la structure et l'organisation du char. Donc vous avez une corrélation ici qui s'appelle le paléothermomètre, qui a été développé par Deldic en 2016, qui est publié dans la revue Carbone. Et vous voyez qu'en fait, ils ont établi une corrélation entre la température et le ratio de ces deux pics. On voit, nous, qu'on suit cette tendance, mais avec une différence quand même relativement significative entre les biochars issus de pyrolyse, de biomasse lignocellulosique et les biochars issus de biomasse non lignocellulosique. Donc encore une fois, il y a une différence assez notable entre ces deux types de biomasse, donc des structures potentiellement des structures chimiques différentes du fait de la différence assez conséquente au départ de la biomasse. On a eu aussi un intérêt pour l'analyse de la matière minérale, donc on s'est intéressé à quantifier les différents minéraux principaux présents dans ces différents biomasses. Donc les 4 biomasses qui contenaient des minéraux de façon assez significative, c'était le digesta, fumier, fiente et rafle de maïs. On a utilisé une technique de mesure semi-quantitative par XRF qui est non destructive et qui permet d'avoir des résultats assez rapides. On est en train de comparer ces résultats avec des analyses par ICP qui sont plus absolues. Les tendances sont les suivantes. La matière minérale a tendance à se concentrer dans le biochar puisqu'elle n'est pas volatilisée. Donc comme on volatilise une grande partie de la matière organique, on concentre les minéraux au sein du biochar. Et on s'est intéressé également à savoir sous quelle forme étaient présents ces minéraux dans les biochars. Donc on a fait des analyses en MEP, donc en microscope à bailliage électronique, et on a couplé ça avec des analyses en XRD pour essayer de voir quelle était la forme cristalline ou la spéciation de ces différents métaux dans le biochar. Donc là vous avez deux exemples. Vous avez un exemple des rafles de maïs par exemple pyrolysées à 500 degrés. Vous voyez qu'on a une concentration assez importante en silice et on observe finalement à cette température des grains de silice dispersés sur les particules de biochar. Ces grains de silice par XRD ont été identifiés comme étant des particules de quartz. Et à 800 degrés, vous voyez que ces mêmes particules, elles se sont organisées selon des filaments. Donc on a concentré en silice notre biochar et la forme qu'a pris cette matière minérale a changé entre 500 et 800 degrés. Une autre analyse, c'était d'étudier aussi la porosité, donc une étude morphologique. Donc on a utilisé deux techniques qui sont assez connues et utilisées dans la littérature. C'est la surface spécifique par azote et la surface spécifique par CO2. Les résultats ont montré que pour les biomasses lignocellulosiques, on avait des porosités autour de 300 et 500 m² par gramme. Alors que pour les biomasses qui contenaient des minéraux, donc principalement les biomasses non lignocellulosiques, on avait des surfaces spécifiques de l'azote qui étaient relativement faibles. On a aussi étudié par une autre méthode qui est surface spécifique mesurée par CO2 et on voit que lorsqu'on augmente la température, on augmente les surfaces spécifiques et par CO2, les biomasses non lignocellulosiques présentent une porosité mais toujours plus faible que celle des biomasses lignocellulosiques. Une autre mission, un objectif de ce projet, c'était d'essayer d'étudier un petit peu quelle est l'interaction du biochar avec l'eau, parce que si on le met dans les sols, on sait qu'on essaie de voir comment le biochar peut absorber et libérer l'eau. Et on a identifié une technique qui s'appelle la RMN, donc résonance magnétique nucléaire par proton, par relaxométrie du proton. Donc l'idée, c'était de voir comment est-ce que l'eau interagit chimiquement ou physiquement avec le biochar. Donc là, vous avez la surface spécifique à 500 et 800 degrés pour deux régimes, pyrolyse lent, pyrolyse rapide. Donc vous voyez qu'avec la température, la surface spécifique augmente. Et lorsqu'on est en pyrolyse rapide, les résultats montrent une surface spécifique plus importante. Ensuite, on a étudié la densité squelettique, c'est-à-dire par porosité à l'hélium. Vous voyez qu'on a les mêmes tendances. Le biochar a tendance, pour le même volume, le biochar a tendance à se densifier. Donc vous avez un biochar qui devient, pour le même volume, qui devient beaucoup plus dense. Et pareil, on a le même effet, ça veut dire une augmentation avec la température et avec le régime pyrolytique. Donc ces biochars, ils ont été après, donc là c'est des résultats pour des biochars de Douglas. Ils ont donc été humidifiés avec de l'eau. On a laissé l'eau rentrer un peu le plus possible dans les différents pores. L'idée de cette technique, c'est que vous mettez votre biochar humidifié dans un champ magnétique et vous mesurez un paramètre qui s'appelle le paramètre de relaxation. Donc si vous avez que de l'eau, vous n'avez aucun effet du champ magnétique sur l'eau, parce qu'il n'y a que de l'eau dans l'aimant. Et vous voyez que pour les biochars en pyrolyse lente et pyrolyse rapide, on a un signal qui est relativement différent de celui de l'eau libre, et on a un signal qui est relativement le même pour qu'on soit en régime pyrolytique lent ou en régime pyrolytique rapide. Donc, ce qui sous-entend une interaction relativement similaire entre ces deux types de biochars. Lorsqu'on chauffe lentement à 800 degrés, on obtient un biochar qui commence à se rapprocher de l'eau libre, donc qui est relativement différent des deux premiers, mais qui reste aussi différent de l'eau libre. Et lorsqu'on est en pyrolyse rapide, à 800 degrés, on a un biochar finalement qui se rapproche, on a une interaction entre l'eau et le biochar qui se rapproche de celle de l'eau libre. Donc c'est une méthode qui a potentiellement un intérêt pour pouvoir quantifier et estimer l'interaction que va avoir l'eau avec le biochar. Un autre point sur lequel on a travaillé, c'est la production de biohuile par pyrolyse rapide. Donc, on est parti sur une technologie qu'on a disponible dans notre laboratoire, qui est un lit fluidisé à 500 degrés, à 1 kg d'injection dans le lit de sable. Le défi était de pouvoir récupérer la phase lourde de biohuile, donc de mettre au point une technique, une méthode de condensation étagée. Ça veut, lorsque vous avez produit des biohuiles de pyrolyse, vous avez en grosso modo 50% d'eau, 50% de phase lourde. Et donc du coup, on a joué sur la température de nos condenseurs pour essayer d'avoir une phase lourde ici, à peu près à 20% en eau, donc qui présente un intérêt assez intéressant en termes de valorisation. On a eu 30 à 40% basique de biohuile lourde, avec 62% de carbone et environ 30% d'hydrogène pour un PCI de 25 kJ par gramme. Et le rendement en biochar était entre 15 et 20% massique pour un carbone fixe de 82%, pour 85% de carbone. Voilà, donc je vous remercie pour votre attention. Si vous avez des questions, je pourrais essayer d'y répondre. Merci.
Merci beaucoup pour cette présentation. Est-ce que c'est possible d'extrapoler ces données pour estimer selon le charbon, biochar ou charbon de bois, je ne sais pas comment le catégoriser, le charbon de terre preta? Est-ce qu'on peut deviner quelle a été la température et les conditions de fabrication de terre preta en fonction des données que vous avez là?
Oui, bien sûr. C'est théoriquement possible, parce que notamment par spectrométrie Raman, comme je l'ai montré, ou en combinant avec le rapport H sur C, on serait capable d'avoir pas une idée exacte, mais une idée au moins du régime pyrolytique qu'il a subi. Est-ce qu'il a quelle température, quelle durée, etc. L'idée en fait qu'on a pour la suite du projet, c'est d'essayer de déterminer un sharing index, ça veut dire une formule de sévérité qui permet de lier température, temps et vitesse avec les caractéristiques du biochar. Par rapport à la stabilité de Terra Preta, la stabilité du biochar va être donnée par son rapport H sur C, par la taille des clusters, etc. Donc si on avait toutes ces données, si je pouvais analyser de ce biochar-là, je pourrais donner des conclusions sur la stabilité de biochar et de comment il a été produit.
Good afternoon, everyone. Thank you for your time. It won't take too much. So I'll take up a subject. I'll talk about a subject which is less scientific and a little bit more engineering. and specifically on the synergies and opportunities from and the integration of anaerobic digestion and pyrolysis. And we'll look at 2 experiences on 2 case studies in Italy where we addressed the organic fraction of municipal solid waste digestion. So we'll have a look at the generalities of this integration process. Product classification will be included, of course, and we'll look at 2 different kinds of integration. So at the back end, so pyrolysis as a post-processing treatment, then anaerobic digestion, and the front-end integration with anaerobic upstream of the digester. And then we'll have a look in a little bit of details, an overview, let's say, of these 2 case studies. The first one is the first plant of this kind in Italy, which has been authorized, in which an organic fraction, let's say a digester operating on this bio-waste stream, will be coupled to a pyrolysis unit. And a very small, on the opposite scale, case studies in a minor island in Italy, in southern Italy, for 1 kiloton per hour, a kiloton per year, that biodigester operating again with a pyrolysis unit. So why biochar? Everyone knows here, so I'll be quick on this, that the advantages that we have is that we will produce a form of carbon that is long-lived, very stable compared to the labile carbon that we can get from the anaerobic digestion processes as such. So there are possibilities that open up to credits and carbon sequestration by applying this process to a bio-waste stream. So how it plays out? Well, we have our very simple, straightforward anaerobic digestion system. So we produce CO2 and methane. You can either separate them or use it as a biogas, you know very well. You get out your digestate from the system, and after the thickening phase, you get the liquid, so straightforward stripping, and you recover some ammonium sulfate. And then with the solid phase, you get out a first potential product, which is a fertilizer product, CMC5. Or if you add some green waste and go for composting, you can go for CMC3. So classical compost. What happens next? If instead of going for composting, we had a dryer and a slow pyrolysis system, well, you can get out biochar, which again, certainly, is another fertilizer product, CMC14. So with clear advantages, of course, in different use cases. So possibilities are there for different uses. And well, one of these clearly is that the stability that we get of the product and the possibility that we have a product that it's no longer used in fertilization of fields, but we can use in carbon sequestration applications. Another possibility with the back-end integration is that you might leverage the properties of biochar and add it to the composting pile and get a compost-enriched biochar or co-composted biochar. Of course, this is just flow chart. Then you have to make the things work when it comes to mass balances, clearly. But again, this is another possibility that opens up by the back-end integration. Alternatively, we can look at the front-end integration. So again, we have on the right-hand side, we have our standard process and possibilities. So either CMC5 or CMC3, not both together, clearly. And a biomass operated slow pyrolysis unit producing a biochar that can be fed in the anaerobic digestion system to improve and boost methane yield under certain conditions, of course. And what you get? You get either a CMC5 enriched in biochar or a CMC3 enriched in biochar, which again opens up possibilities and provides additionalities. One of these, of course, is carbon storage and sequestration. The other is, for the CMC3, for example, that you improve the composting process. So you get some benefits if compost is the process you're looking at. Let's see briefly these 2 case studies in which pyrolysis was first authorized in Italy in a process that treats bio-waste, so not a process operating on a clean biomass as we know it. So this plant has been authorized in 2024, operates on a roughly 40,000 ton per year of bio-waste, separately collected from the local municipalities, and a couple of thousand tons of green waste, so shrubs, prunings from trees on the streets. Of course, the process in this specific case is biomethane, which is reinjected into the grid, and CO2, which is sold separately, and then biochar, and of course ammonium sulfate, a technical grade ammonium sulfate. It seems very simple in terms of a process flow chart, but you know, devil is in the details. And when it comes to authorizing such a plant in our country, legislation plays a role. And given that you're not processing a clean biomass, or you're processing, unfortunately, a bio-waste, and as such, legislators ask modification to this kind of process. So what happens here is that merely due to regulatory constraints, what you have to add is a pyrogas cleaning step before oxidizing the pyrogas. As you know, the vast majority, let's say overwhelming majorities of technical pyrolysis installation burn off all the pyrolysis gases as they are. A limited number of installation condensate the pyrolysis gases to get out some liquid, but really the vast majority just straight burn them. Now, in Italy, due to the national legislation, so it's statutory obligations, the majority of the regulators does not allow that, or allows that under the condition that you treat this section, so the pyrolysis section, as an incinerator. They make this equivalence. So you have the burden to sustain of all the analysis that you might need to apply and deploy to an incineration plant. So in order to avoid this, you have to purify the pyrolysis gas stream. Purification for them means removing the organic compounds, or leaving just the clean syngas available. And this is why in this specific project that was authorized for construction in 2024, we needed to add this pyrogas cleaning step. On a different take for this other project that we've been doing for the municipality, though, this small island in Pantelleria is an island located in the middle of the Mediterranean Sea between Italy and Africa, in Italy and Tunisia. Roughly 10,000 people living there all the year. So it's a very, very small project. And basically, with a very large fluctuation between seasonality of production of green waste or bio-waste due to the influx of tourists, clearly. So we had to be creative in addressing this specific need. And we had to resort to a modular anaerobic digestion plant, which is made in France, by the way, by a very nice company, B&Co. And in order to adjust with a fluctuation of this load and make the pyrolysis section to work as constantly as possible with a smoother flow, we had to add some green waste to make up for the fluctuation of the bio-waste. So in order to have a good anaerobic digestion system that can handle with modularity the fluctuation in bio-waste, and with green waste, we make up this fluctuation to have the pyrolysis unit running, let's say, constantly, a constant load all over the year. Again, you won't see much changing. Still, we need to add this scrubbing and condensation step on the pyrolysis gases that, in this specific case, are not burnt directly, but are sent to a cogeneration system. So, due to the local constraints, all the system has to run on electricity, and there was a significant amount of PV panels installed to make up for the consumptions, and the separated phase can go then to the wastewater treatment, which is nearby. So the plant is expected to roughly, as I mentioned, as an overcapacity of up to 1.3 kiloton per year of organic fraction of municipal solid waste. The makeup green waste is roughly 10,000 tons per year, something in that order. And this plant is expected to come online in 2026 in the Isle of Pantelleria. So again, the product will be biogas and syngas that will be used in co-feeding in the cogeneration sections in the engines, and A peculiarity of this system is that the drying stage of the digest state will be an heat pump dryer in order not to have stack emissions, but to treat the water in the wastewater treatment plant that, as I mentioned, is located nearby this installation. And concluding this brief overview, well, Biochar has the potential to turn bio-waste digest state into a much more stable and durable carbon-negative soil conditioner. And as such, roughly half of the carbon that we get into the biomass can end up in the biochar, and in a much more stable form, so in a long-lived form. There are multiple options for the pyrolysis plant layout, so condensation and cogeneration or full oxidation of pyrolysis gases depending on the feedstock and local regulatory constraints. But again, regulation might require to compromise on plant configuration and might play a role. And this is absolutely dependent on local conditions. When it comes to integration, when added to the back end, along with composting, Biochar can decrease nitrogen emission in the stack, increasing composting speed and product quality. So you get out some value out of it. One of the problems that we have with the bio-waste digest state is that its value is practically nothing, zero. Digest state can change this economics. You can change the economics of the system, adding a value and thus decreasing the cost due to the improved composting speed. When added to the back end instead of composting, of course you have less burden of civil works because the composting phase is, say, civil construction works intensive. You increase the value of products much more because you retail biochar for at least a couple of €100 per tons. Conversely, as I mentioned, the digested value is practically nothing. And of course, you open up to carbon sequestration. Conversely, when added to the front end, you can improve biomethane yield, or in general, methane yield, and thus revenues, and produce a biochar enhanced fertilizer product at the very end of the system, so either CMC3 or CM3-5. So thank you much for your attention, and I'll leave the floor to the next speaker.
So thank you everyone for still being here at the end of a second long day of conferences. I am going to be a lot less technical than my predecessors. I am here to talk about carbon strategy. So I work with Geca, and what we do is we accompany project developers, especially in biochar, but also in bio-oil, any waste treatment through thermal processing to get carbon sequestration and carbon credits. So we advise on technical issues such as choosing the right machinery, the right equipment, finding the right recipe for biochar, and then we can advise you on developing the carbon strategy. So we, on the carbon side, which is the team I work in, we help you find the right narrative for your project. So we take care of writing the project design documents. We take care of writing the LCA. We only ask you to collect the data in order to get the certification. We can also help you choose the right standard, because this is a tricky part. So what I wanted to do today was to present a specific project we have that is currently issuing credits. It's a 20-year-old company that manufactures waste treatment solutions for manure in the United States. The machinery is available worldwide, but the site, the facility that is currently certified is in Indiana. Their machinery is specialized in non-wood organic gasifications. So their pilot project was for poultry and swine manure in Indiana. The maximum transportation within the facility from the biomass collection into the biochar application is 4 miles. They are an example of perfect circularity. The fresh manure is collected daily from the farm. It is then dried at around 300 degrees Celsius. Then it goes through the process of gasification with an output of 1.8 ton per hour. Then it goes through packaging, storage, and it is then later used on site. So from a carbon strategy perspective, what are the challenges? What are the opportunities? In terms of challenges, it is a wetter feedstock than woody biomass. It requires then energy consumption in order to go through drying and then gasification. It has a lower carbon content than woody biomass. It has a high price point, and there is a certain misunderstanding from buyers, carbon credit buyers, surrounding biochar credits for manure. They are concerned that with contaminants and taking manure that could be applied in fields. However, the opportunities is we obtain carbon credits. This project is the first project to obtain biochar sequestration carbon credits under Pure Earth. It has unlimited feedstock. Biomass availability is not an issue for this project. There is an opportunity in tipping fees, because for this specific project, that's not the case, but in the other projects this Earthcare is developing, they will obtain tipping fees to allow the farmers to get rid of the manure. And one of the great advantages of this project is it is an established company. It has been existing for 20 years. So we started working with Earthcare in 2022. First, we worked on making sure that the biochar they were producing respected the criteria for carbon credits. Then we worked on carbon advisory and strategy. We gathered the data that we collected during the production period. We wrote the LCA, we wrote the PDD, we found buyers who were interested in the narrative. This allowed us to get the issuance in November 2024. The first sale of carbon credits from this project happened less than a month later. The next issuance is for end of Q1 2025. Once the project goes through the first audit, it goes quite fast. So what's the narrative of this project? Well, first, it's North American. It's very USA. It's Indiana, farmers in Indiana. Again, it's an established company, 20-year company that made its success in waste treatment before talking about biochar, reassures buyers of carbon credits significantly. The team is experienced. The leaders of Earthcare each have around 30 to 40 years experience in this industry. They have multiple streams of revenue. Earthcare manufactures equipment. That's what they sell. They come to a site, install the equipment, and then they create a partnership with the farmer to share the carbon credits. So another aspect of narrative is co-benefits. When we apply biochar in soil, it is relevant to talk about increase in yield. This is often targeted under SDG 2. However, SDG 2 targets smallholders, small farmers in Global South. It is important to check the details of an SDG because the increase in yield is extremely relevant. But as we saw a bit earlier in the presentation of my predecessors, it depends where you apply the biochar. Not the biochar applied worldwide will have the same increase in yield. However, Earthcare is a perfect example of SDG 12. Circularity, reduce in waste. And they help soil rehabilitation. They can, depending on where they are located. What's the future for Earthcare? Currently, they have one facility issuing credits. They currently have 3 sites collecting data, and that will go through their first audit within the next year. They have 5 sites currently under construction that will issue credits within the next 2 years. They have contracted 30 facilities that will issue carbon credits. once you get the first site certified, it can go quite fast. Again, what are their advantages? Well, their feedstock is out of the ordinary. They are the first manual biochar credits to be certified and sold. They are small. The machinery and with the amount of feedstock they can go through is reasonably small. Farmers do not need 50,000 tons of feedstock. They are very small, but they're replicable. They have an experienced team, access to feedstock, and the use of the biochar is on site. Again, we are in perfect circularity. They are not concerned about using the biochar, which is a key issue we have as when we help project developers. You do not need to only focus on producing the biochar, you need to make sure it is applied. Otherwise, you're not eligible to carbon credits. Thank you.
Yeah, there is no proper moderator here on this panel, but just we are through with the 5 presentations, and just the question again, are there any questions from the audience to the presentations?
Thank you very much. I have a question for my colleague from France in français. Pour les charbons, les biochars à 500 et à 800, est-ce qu'à la fin, vous faites une comparaison, en termes de comparaison, est-ce qu'on peut dire que la température elle a vraiment un effet? Et si oui, quelle est la température optimale peut-être à laquelle on peut dire que le biochar peut répondre à des besoins qu'on vous avez spécifiés? J'ai une deuxième question, si vous le permettez, sur l'analyse de la partie minérale. Est-ce que, bon, j'ai vu les éléments, mais de plus en plus, on ne parle, pourquoi est-ce qu'on n'analyse pas la radioactivité de ces biochars, justement, qui peut devenir un élément aussi peut-être à considérer lorsqu'on réutilise ces biochars qui proviennent peut-être d'une biomasse d'un site qui peut être contaminé dans un site qui n'est peut-être pas contaminé. Donc on risque de le contaminer par le biochar. Est-ce que c'est des choses auxquelles vous avez pensé? La dernière question, c'est par rapport à la caractérisation des biochars. Peut-être j'ai pensé un petit peu d'une manière en tant que chimiste. Est-ce que l'infrarouge ne nous apporte pas peut-être des éléments d'information supplémentaires dans la caractérisation? Merci.
Merci pour votre question. Donc pour la première question, en fait, la température, c'est le paramètre le plus important pour déterminer la composition élémentaire ou même physique du biochar. Donc c'est un des paramètres les plus importants. On a considéré principalement celui-là. Après, vous pouvez aussi ajouter le temps et la vitesse à laquelle vous chauffez le biochar, mais dans une approche globale de sévérité, d'indice de sévérité, c'est la température qui est vraiment, vraiment importante. La deuxième question sur la radioactivité, non, on n'a pas d'éléments radioactifs dedans. On n'a pas mesuré, mais on n'avait pas d'intérêt à le faire pour ce type de biochar. Et la troisième question, donc du coup sur l'infrarouge, je ne vous ai pas présenté les résultats, mais effectivement, alors le problème dans l'infrarouge, c'est qu'à 800 degrés, vous avez quasiment plus de signal parce que c'est que du carbone, très peu de fonctions de surface. À 500 degrés, par contre, on a fait de l'infrarouge et par analyse ACP, donc statistique, vous pouvez retrouver l'origine du biochar en fonction du signal d'infrarouge. Donc l'infrarouge, c'est une analyse assez intéressante parce qu'elle est très rapide et bon, elle n'est pas quantitative, mais elle vous permet après, par analyse statistique, de savoir un petit peu d'où provient votre biochar et comment il a été pyrolysé.
Merci. Une question pour vous encore une fois. La température est très importante. Que va changer la durée d'exposition au biochar? Qu'est-ce que ça va changer dans les paramètres, je sais pas, la porosité, la contenu en carbone, etc. Quelles vont être les différences?
Alors pour nous, dans nos conditions, il n'y a pas vraiment de différence. On est sur des temps de résidence à température fixe assez courtes. Hein. On a chauffé à 10 degrés minutes, puis on a arrêté, et on a chauffé très rapidement, puis on a laissé un palier de 10 minutes. Donc on est sur des temps très courts. De ce qu'on sait de la littérature, c'est que le temps a pas vraiment de, enfin, il a eu un impact, mais qui n'est pas forcément significatif, du moins par rapport à la température. Et pour la porosité, ça va plus être comment est-ce que vous avez chauffé votre particule, parce qu'en fait, en pyrolyse lente, vous allez laisser le temps au volatile de s'échapper de la structure du bois. Donc vous allez retrouver quasiment la même structure au départ que la structure de départ, si vous regardez les pores par exemple du bois. Par contre, si vous chauffez à pyrolyse rapide, comme vous allez générer beaucoup de volatiles d'un coup, vous allez éclater en fait la structure cellulaire et vous allez créer finalement des pores, vous allez créer des défauts, etc. Donc c'est pour ça que le résultat qu'on a obtenu en interaction avec l'eau, pour les pyrolyses rapides à très haute température, la structure finalement du char elle est complètement défaite, complètement détériorée. Ce qui fait qu'on a un biochar avec des très gros trous, des très grosses imperfections. Et là, on a un biochar qui n'a pas du tout la même structure physique qu'un biochar chauffé très, très, très lentement, qui a conservé finalement sa structure originelle.
Et quel impact ça peut avoir du coup sur la rétention d'eau ou des minéraux par exemple? Est-ce qu'il y en a un qui est mieux que l'autre? Question un peu bête.
L'eau, si vous avez plus d'espace, vous allez avoir plus d'eau à l'intérieur parce que vous avez plus d'espace. Mais l'eau ne sera pas en interaction forcément avec le char. Donc elle va pouvoir diffuser plus rapidement ou être larguée plus facilement. Et ensuite, l'interaction, en fait, on s'est rendu compte que l'interaction entre l'eau et le biochar, elle se fait à la fois entre la structure carbonée et l'eau, et elle se fait aussi avec les minéraux qui sont présents au sein de la structure. Donc en fonction de comment ces minéraux sont disponibles dans le biochar, ce qui est difficile à connaître puisqu'on voit souvent ce qui est en surface, en fonction de comment ces minéraux sont accessibles, vous allez avoir une interaction qui peut augmenter.
Et du coup, il vaut mieux la structure identique à l'état original ou la structure éclatée, ou il n'y a pas vraiment de réponse?
Alors si vous voulez par exemple une résistance mécanique, vaut mieux regarder, pour le bois en tout cas, on a fait des tests là-dessus aussi, je n'ai pas montré les résultats, mais de mémoire, vaut mieux garder la structure originale.
Ok, merci.
Oui, on a souvent entendu dire que le charbon de bois, je ne parle pas de biochar, que le charbon de bois est toxique parce qu'il y a des substances pyrolytiques dedans. Est-ce que vous pouvez confirmer?
Ça veut dire que ça peut relarguer des molécules aromatiques, des HAP, ce qu'on appelle, c'est ça?
Mais j'ai toujours entendu dire que, par exemple, il ne faut pas vivre près d'une fabrication de charbon de bois parce que des fumées sont... je ne sais pas si le pyrène ou le benzène ou quoi, mais il y a des produits aromatiques qui sont mauvais.
En fonction de le temps de résidence des vapeurs dans le réacteur, vous allez former des suies qui peuvent forcément être toxiques pour la... Mais dans le biochar, il peut y en avoir aussi, surtout sur les biochars produits à faible température.
À faible température.
In fact, I have one more question to my colleague from Italy. The digestate is a very wet matter with a low solid content. And you mentioned that most of the pyrolysis installation nowadays, they just burn the syngases on the spot. So in principle, there's energy available. My presentation was also about that part. The digestate needs to be dried before pyrolysis. Do you have any? Have you run any rough calculation or energy and mass balance? So how much energy, or is the energy sufficient, or do you need, in fact, even energy from outside for drying?
Thank you for the question. Normally, if you have a very good thickening stage and the digestate is not exceedingly high in hash content, you have enough organics to, let's say, balance the drying requirement with a good dryer, which comes at a cost, of course. Because a very good technical dryer can go, let's say, down to 820 kilowatt hour per ton of water evaporated. A sheet dryer can go 1.15 kilowatt hour per ton of water evaporated. So there's a huge difference in terms of energy demand overall. And with a very good dryer and a reasonable quality of digestate, you can balance the demand. Yes, definitely. But you have to invest, because a good dryer costs double this, roughly twice of average low performance dryer. So it comes down a lot on costs. And in this respect, the addition of green waste prior to pyrolysis is beneficial, because you bring low hash, high carbon feedstock. So you increase the amount of volatiles that you generate. Of course, you improve a little bit the yield. You dilute the hashes if you want, no, in the end product, and thus you can recover more energy. Yeah, definitely.
Thank you.
Thank you. Also, my question is for the colleague from Italy. If I understand that from the Digista to the Biochar, you are not allowed to do it in the past. From the Digista to Biochar, to convert it, if I understand that you are allowed to do that in 2024.
Well, yeah, that was the plant. The plant has been authorized in 2024. The plant, the overall. Okay. It's a waste management facility, you know. So this waste management facility has been authorized by the local authority, regulation authority, and you can do biochar, which is a CMC 15, and under the current regulation, country fertilizer regulation, European fertilizer regulation, starting from organic fraction of municipal solid waste separately collected, either with addition of biomass before pyrolysis or not, plain biodigested, but you can produce biochar under the current European regulations. My point was more on the local national regulation when it comes to how to categorize, how to classify this installation, which is does not deal with the product, but the facility per se. Yeah. And under that's the only constraint.
And in this case, I mean, the regulation is not the same in all Europe countries, no?
When it comes to the product, yes, it is. When it comes to the facility, let's say, besides the best available technologies, it comes down to the local regulation, how you classify a plant. So maybe this approach that in Italy they take is nonsense for other countries. Can be, I hope so, frankly speaking. But in Italy, this is the way, unfortunately.
Okay, thank you.
Well, if there are not any more questions, then I take the freedom to close this session. And thank you also, my co-speakers. Thank you for being here. Thank you. Goodbye.